Hey everybody, and welcome to another edition of Probably Private Red Teaming. And today we're going to talk about adversarial examples. Even though adversarial examples aren't as useful as they were, let's say, 7 years ago, I think it's still really important to understand how they work because we can utilize some of the things about the adversarialness and dream up new types of attacks. So we're going to first explore what are adversarial examples. There was this really cool one that came out now 7 years ago, and I'm going to show it to you. This was a turtle, a 3D printed turtle. And the original turtle, as you can see here, is classified as a turtle. And this was like the best computer vision we had at the time. Then the rifle turtle, which was 3D printed with this adversarial texture, is a rifle. We see it as a turtle. Adversarial examples were really hot then. So there was whole parts of all of the machine learning conferences that were just dedicated to, oh no, we have this problem of adversarial examples. How do we deal with them? So what you're going to learn today, what we're going to go through today is in the notebook, we're going to extras adversarial examples. And what we're gonna check out is how do we build our own adversarial examples. And again, this isn't as effective with today's machine learning models, which we're gonna go over why. Basically, what I want you to understand is adversarial examples are a way of exploiting how deep learning works, how it learns, and what is stored in the model for an adversarial advantage. And the reason why it works is because when we have deep learning networks and these AI models, there is always, again, these decision boundaries to play with. And if we can get near decision boundaries, we can cause uncertainty. And if we can cause uncertainty, we can often either cause misclassification or at least instability, so to speak, in the network decision process. And that's our goal as an attacker with adversarial examples is, can we get to an instability where we essentially can make the machine learning make an incorrect decision when if a human looked at it or if a human reviewed it, they might actually know what we mean. So we kind of slip by the human filter and we exploit the fact that deep learning has these interesting properties. Okay, so this is going to use some other libraries, some stuff that is a little old. So I apologize. I first ran this notebook as a class I built for O'Reilly now many years ago. And you know what? It still works. So we're going with it, okay? And we're going to use some older deep learning models. And this is because obviously they're a wee bit easier to attack. And here I'm loading in ImageNet, which if you don't know is one of the classic deep learning image data sets. And I think for adversarial examples, it's really fun to focus on images because we can see the attack. And for a long time, it was really hard to create reasonable adversarial text, although that is now changing. So we'll talk more about that. So we're going to load ResNet 50, which is a model. If you haven't ever loaded it before, this will take some time for you to load. And we're just going to take a look at one of the images from ImageNet. Here we have a cat. We see that we also get it classified correctly. It's not a tabby, but at least we're in the cat zone. And this is just like classic, how do you load images and put it into a deep learning model? And we're using a Keras model here. So ideally you would pause right now and just to practice, you would take this code. You can take a look in the data and images folder. So we can look at data images folder and you can see there's a bunch of stuff in there. Whatever you want to load something. I chose the shark. So if you want to load the shark, load the shark. But I just want to make sure that you know how to kind of take that, transform it into information that we can send to a deep learning model. And now we're going to initialize a model called a FoolBox model. Now, FoolBox is a library for generating adversarial images. I had a look around. It looks like it's still kind of maintained, but we're going to hope that it's maintained long enough. So FoolBox has a bunch of different attacks. It was a library that was really popular when it came out for quite a while, of building adversarial attacks against these systems. And yeah, we get a deprecated version, but we have now our FoolBox model, which is really going to act as a wrapper around the main model. And what this is going to try to do is send things to the main model, learn how the main model is working, and then devise attacks based off of that. So now we're going to run through some examples. We see we get 87.5 on the data set that we have of accuracy. That's without the adversarial attacks. Okay, so we have like a good idea. Our model is pretty good. It's not amazing, but it's pretty good. Now we're going to use the fast gradient sign method attack. So this was kind of one of the first really big attacks. It was researched by some folks at Google, so you can check out the paper here. It was a really cool paper when it came out. Ian Goodfellow, whose book I still recommend if you want to learn deep learning. Ian Goodfellow's book is amazing. Highly recommend. But it was this really cool attack where they essentially exploited the second derivative of what the gradients are in order to find essentially boundaries. So essentially, where do we think on this image with this model would be a useful place to shift the decision? And you can try to think of this because at the time, people were trying to develop like single pixel attacks. Could we change one pixel and completely change the behavior or the output of the model? And so looking for the most at risk, the most vulnerable parts of the image, and then let's put noise in there that essentially increases the error on this particular example. And if we can increase the error on this example, either pushing it towards another decision boundary or just creating instability, then we can get this behavior that we want. As a very high level, read the paper for more, or let me know questions that you have. Trying to keep the theory to understandable bits, but you give me feedback of how it's working for you. And now we're going to run the attack. And what I've done here is I've chosen different epsilons, and the epsilons say the amount of noise. So from an attacker perspective, we want the least amount of noise for the highest attack reward. So we want to find the smallest noise that we need to get the reaction that we want. And this is because obviously when we start thinking about defenses, one possibility is let's just denoise things that are coming in that we think are noisy. And if we could do this, well, we could prevent all of the attacks, right? Okay, so let's find what successes we have. Yours might be different. So take a look through yours. We essentially have an array mask here, which is a nice thing that we can use to say which attacks worked and have a look. So here we can see here's one row from my first epsilon. There's another row from my second epsilon. There's another row from my third epsilon. And we see that the higher the noise, the more attacks go through. So here I've picked out one of them, right? So I'm in the third attack first image. So I'm here at this one. You play around. Pick whatever one you want. Have a look, okay? Iterate through all of them. Here we can see we have our original one. We have our adversarial. I'm going to zoom in. That still looks, I mean, I am just a mere human. But you can see this is pretty darn good. So we have this difference, right? And we can see obviously some interesting things are happening at the back of this, right? We can see that we have some interesting noise patterns around. That's our difference. Take a look. I'd be very curious. You can happily post some images in the comments of how it went for you. And then we want to take a look. What's the predicted label? So it got it wrong, but what does it think this is? So I want you to try. So if you're trying, I want you here. We have the adversarial X, the image X. I want you to predict. So pause it if you don't want to see the solution. Now we have the solution. We're going to go through. We see that the adversarial predictions are that it's a dining table, and the original that it's a folding chair. And we see we've basically flipped these predictions. So now it's 80% sure it's a dining table. And before it was nearly 98% sure it's a folding chair, and then dining table was just this nearby mistake that we could exploit. There's numerous other attacks in FoolBox. So give fast gradient sign method a try, because I think it's a super fun and usually pretty fast one. But take a look at the other attacks. I have also some example code here for potentially trying to drive it towards a different criteria. So you can also look through the criteria. You can choose a target class. See, for example, if you can turn a dog into a cat or something like this, right? Try to play around with it. And the reason why I want you to play around with it is because I think you're going to learn more about deep learning, and you're going to have maybe some fun doing so. So you might be wondering, Catherine, you told us you would say why adversarial examples aren't so popular anymore. Here's a little history lesson. So there was a bunch of really cool solutions that were proposed, like compression, understanding noise, and, removing noise and all of these things. So in fact, there's some really cool research, and I'll put it in the description, around how you can use a diffusion model to slowly remove adversarial noise, which is pretty darn cool. What they found, or what ended up being kind of the easiest way to deal with adversarial examples, was to just train on them. So increase your model size and train and train and train on noisy examples. I don't know if you're old enough to remember the Google CAPTCHAs where it was like really weird and noisy for a while there. Like you felt like you were in like a pixel video game trying to click where's the stop sign and stuff like that. But that was during these times of let's scale up model size with adversarial training is what it's called. And I'll put a link to some of the research, and also I have an earlier video on adversarial examples and what they teach us about the memorization problem. So take a look at that too. But what we essentially said is, look, let's create a way larger model. Also, we have probably way larger distances between decision boundaries. And let's also add to that a bunch of noise. So now we have some essentially built-in robustness. Like we expect some noise, and we want it to be a part of how the model learns. Like when we give it a noisy folding chair, we want it to know that that's still a folding chair. And in doing so, created this kind of race for larger models, which of course created some of the overparameterization that we end up seeing today. So it's kind of a large-scale movement towards bigger and bigger models in an effort to get more robustness, in an effort to maybe also get better performance, and that all culminating in the extremely large models that we see today, which are also fairly robust in comparison with the smaller models that we had because of this extremely large decision space in comparison and the many, many layers in comparison. And this is why, so one example, this is why if you put a typo in an LLM, it doesn't get confused, because typos are now just part of the training data, and noise is a part of the training data. And we're going to talk more about the training data next week. We're going to try to think and figure out Are there ways that we can exploit what we know about the training data and how the models are trained to extract more information from the models themselves? More on that next week. But let me know, how do you like playing around with adversarial examples? Maybe post some. If you got it running on your computer, post some that you like. And happy to hear from you how you like this little mixture of theory and practice in this video this week. All right, see you next week.